Good afternoon, ladies and gentlemen, distinguished guests. My name is Ming-Shu Xie. I'm the Director of Quantum Computing Research Center at Foxconn. It's great, with great honor today and that we welcome our distinguished guest, Professor Alain Aspect, Nobel laureate in physics in 2022. Professor Aspect is a pioneer in the field of quantum physics, whose groundbreaking work has transformed our understanding of the quantum world and inspired generations of scientists. His remarkable contribution not only advanced fundamental research, but has also driven the applications of quantum technologies, opening up incredible possibilities for the future. Today, Professor Aspect will be speaking on the topic quantum technologies from basic research to applications. I'm confident that his insight will not only enrich our knowledge, but also inspire us to explore how the cutting-edge technologies can be harnessed to shape our world and the future. So ladies and gentlemen, with no further ado, please join me in giving a warm welcome to Professor Alain Aspect. And before Professor Aspect to start his speech, we, Foxconn, prepare a small present to welcome him.
Surprised to receive a gift because I understand that it is the birthday of Foxconn today, so it should be me giving a present to Foxconn. Okay.
So the present here is the best gift to us.
Okay. So anyway, happy birthday, Foxconn. I have no doubt on the expertise of Foxconn people. Okay. Okay, it's a real pleasure to be here, and decades ago, if somebody had told me that one day I would be in front of investors, I would not have believed it, because all my life I did basic research, but also I understood very early in my life that if basic research finds some application, is yet better. Because, I'm very interested in money, and the point is the following. If your application work, then there is a lot of taxes, and taxes are good to subsidize basic research. So I think that it is a good idea to help development of applications. And what I want to show you today, probably many of you know it, but in case you don't know it, is that there is always a path from basic concepts to applications, but it is a long way to go. And of course, rather than a general talk, it will be on the subject which I know, which is quantum technologies. So I will start with what I call the great picture, big word, to just put the context. Then I will speak about the state of the art and open questions in quantum technologies, and make a comment about, we can read many things about the quantum advantage, so I will comment a little bit of what might be the quantum advantage. Okay, let us start with the great picture. And my vision of the applications of quantum physics is that we have two great quantum mysteries for two quantum revolutions, the first and second quantum revolution. The first extraordinary property is wave-particle duality for a single particle. You have a particle. You think you know what is a particle. It has a trajectory, but it is also a wave. This is extremely mysterious if you think of it, okay? And so there were plenty of discussion. So a particle also behaves as a wave. A wave can also behave as a particle. For instance, when you have light, it can behave as particles called photons. But it's extraordinary, it's difficult to understand, but if you take each of these two visions, each one you understand what it is, okay? You have a particle and a trajectory, we understand it. You have a wave propagating, you understand it. You have classical model for each of the aspects. What is bizarre and strange is the same object can be both a particle and a wave. The second extraordinary concept is entanglement. And there we don't have any reasonable picture for that. Entanglement is about two particles which can be in a state such that you can no longer think individually of each particle. So if the two particles are inside an atom, for instance, two electrons in the helium atom, that's okay, it's a single system. But the genius of Einstein, with colleagues Podolsky and Rosen, was to understand that according to the equations of quantum physics, even if the two particles are far away, they keep this kind of unique property. They are separated, but anyway, you can not think of the system as made of one thing here and one thing there. It's something kind of global. And one way, and so it's very difficult to make an image in our own world. One way of doing it, which is not accepted by all my colleagues, but which I like, but I don't demand anybody to accept my point of view. But my point of view is I accept the notion of non-locality. That is to say, I accept the idea that the two particles are instantaneously in common interaction, whatever it means. I have this image in my head, and it happens that this image is extremely fruitful. Okay. A few words about the first quantum revolution. What was it? So, a revolutionary concept, wave-particle duality. It allowed scientists to understand the stability of matter. Do you realize that by the end of the 19th century, physics was very advanced at the end of the 19th century. Anyway, they could not understand why matter is stable. And the reason is very simple. They knew that matter is made of positive and negative charges. Positive and negative charges attract each other. So matter should collapse on itself. And the reason why it doesn't collapse is because the electron, which would fall on the nucleus if it was a satellite, it would eventually fall on the Earth. The electron that would fall on the nucleus is also a wave. And a wave, you cannot squeeze it to a very small dimension. And so it is because of the wave nature of the electron that the electron remains at a certain distance of the nucleus, and this is the ultimate reason why matter is stable. And so quantum mechanics allows to understand stability of matter, chemical bonds, electrical, optical, mechanical properties of matter. It allowed also to understand strange and exotic properties like superfluidity, superconductivity, Bose-Einstein condensation, etc. So this was a scientific revolution, that is to say that scientists understand better the world. Then you had applications, transistor, laser, integrated circuits. Don't think that it was invented by a guy in a garage in California or in China or anywhere in the world. It was invented by the best scientists, the best physicists, trying to describe with quantum mechanics the way the electron move in matter. And eventually they invented the transistor. When trying to understand with quantum physics the way light is emitted or absorbed by matter, they invented the laser, okay? And well, you are all aware that many young people don't realize that when I was young, there was no internet, there was no, it wasn't the first transistor when I was young, okay? And so it has really totally changed the world. Now what I want to show you is some dates. Establishing the quantum theory took about 25 years. It started in 1900 with Planck, then 5 years later Einstein, and by 1925 we have the formalism that we still use, the formalism of Schrödinger or Heisenberg, and so it took 25 years. Now applications. Transistor, 1947. Integrated circuits, 1959. Laser, 1960. And the real development of the Society of Information and Communication, let's say circa 1990. And now we are fully in it. So you see, it takes decades. So I'm sorry to say to investors, you have to be patient. Okay. But if you're patient, it pays off. The second quantum revolution. In fact, it's based on two things. First, entanglement, which is a revolutionary concept, as I told you. And this concept was guessed by Einstein and his colleagues in 1935. It was about discussion on the foundation of quantum mechanics, discussion with Bohr. They disagreed. And in order to foster the discussion, Einstein discovered a new situation, entanglement, the situation of two entangled particles. And again, his genius was to realize that this quantum property would survive at large distance, okay? And there were discussions with Bohr and Schrödinger. At that time, it was only a philosophical discussion about interpretation of quantum mechanics. Everybody agreed on the way to do the calculation. And then, later, I will show you the dates, John Bell discovered that according to the position you take, either the point of view of Einstein or the point of view of Bohr, you have different predictions. So you can settle the debate between Bohr and Einstein by doing an experiment. These experiments were done by, I only cite the Nobel laureates, John Clauser, myself, and Anton Zeilinger, and many other, of course. But there is only 3 Nobel laureates, unfortunately for the other ones. It took some time also for suggestion by Feynman, Deutsch, and other people that this can be used for something. But when I speak of the second quantum revolution, it's not only about entanglement. It's also about the fact that physicists, experimentalists, at one point became able to observe, attract, and manipulate single quantum objects. You must realize that in the early days of quantum mechanics, but early days going until 1960, okay, but people thought that you cannot isolate, you cannot observe a single quantum object. All you can do is have a large ensemble, and then you calculate how this large ensemble reacts. For instance, you have many atoms, you send light on it, and you see the emitted light. And so, with that, they thought that quantum mechanics was about that, okay? But then, at one point, physicists became able to observe, trap, manipulate single quantum objects, single electron, single atoms, single photons, etc., etc. And even, a little recently, they have been able to build artificial circuits which behave as a single artificial quantum object with supraconducting circuits and stuff like that. Okay. Now, once again, dates. So, another stuff, dates. So, entanglement, Einstein, Podolsky, Rosen, Bohr, Schrödinger, 1935. 29 years later, Bell realized that it is not only philosophy, but it is experimental physics. There is a way to settle the debate by experiment. Until that point, everybody thought that it was just discussing, but no real practical debate. 1972, John Clauser did the first experiment. 1982, I presented my experiment, which was directly showing non-locality. That is to say the fact that I have my two particles, it was two photons in my case, they go far from each other, well, far. I had a lab 13 meters long, so I say it goes 6 meters on one side, 6 meters on the other side. And at the very last moment, I set my measurement. That is to say, the measuring apparatus, I change the setting of the measuring apparatus while the photon is flying between the source and the detector. At the last moment, I put like that. At the last moment, I choose the other one, and the final result depends on the position at the last moment. And this establishes non-locality. And then Anton Zeilinger developed several new applications. And so applications started with a proposal by Feynman in 1982, then David Deutsch, and then many, many others. So you see, once again, manipulation of simple quantum objects started in 1970 with the manipulation of single electrons by Hans Dehmelt. And so you see, here again, many, many decades. Okay, at this point, what I am interested in is quantum technologies, application of these ideas at the root of the second quantum revolution. So I will rapidly give some, well, my point of view on where are we with these applications. Let us start with quantum computing. Everybody dreams of a universal quantum computer. If we could have 100 ideal qubits entangled, it would be enough to do all we can think of. You are going to tell me, well, 100 is not much. No. The point is that the size of the mathematical space in which you work increases exponentially with the number of qubits. So I just show you. When I have two entangled particles, the space in which I describe the system has dimension 4, because if I look at the bases, a qubit is 0 or 1. So the basis is 0, 0, 0, 1, 1, 0, or 1, 1. So dimension is 4. If I have 3 qubits, the dimension is 8. If I have 4 qubits, the dimension is not 16. Not very impressive. But think of the story of the grain of corn on the square board, okay? 10 to the 100 is a number that I think nobody can think of. It's the 10 to the power 100 is impossible to understand. It's huge, which means that if I have 100 entangled qubits, the amount of information which is stored in just one state of the system is absolutely enormous. And if now I have a transformation of that state, in that single transformation, I transform in parallel all these data. And so the idea of the universal quantum computer is massive parallelism. Now we have a problem. An ideal qubit does not exist. Well, a classical qubit does not exist either. So what do you do when something is not ideal? You correct. So for classical qubits, there is error correction codes. It turns out that you also have error correction codes with quantum bits. But the price to pay is very heavy. We are not sure, but at the moment, the price to pay is of the order of 1,000 for one. I mean, you need 1,000 of the best qubits we have now in the lab to emulate a single perfect qubit. So if you want 100, you need 100,000. Nobody has 100,000 excellent, outstanding qubits. So we don't know. Will it work? Who knows? I will tell you my opinion on that, right? Well, I can tell you my opinion immediately because it is written here. According to my experience, unfortunately, I am old enough that I have seen many things. For instance, gravitational wave detections. At the end of the 1990s, it sounded totally crazy because it demanded extraordinary mirrors. Nobody had such mirror. It demanded interferometer 4 kilometers long. Nobody thought it was possible to build that, etc. I belong to a committee which eventually decided to build such an interferometer jointly with Italy, between France and Italy, and I voted for it with the argument there is no fundamental physics law that says that it is not possible. And when there is no fundamental physical law saying that it is not possible, sooner or later the engineers do it. Engineers are extremely smart people. If you tell them, look, you can go there, eventually they go there. So I think that sooner or later we will have such a computer. But I don't tell you when, because I don't know. There are questions all the time. Oh, Professor Aspe, you are an expert. On which kind of qubit should we put our money? I have no idea. You have ions, neutral atoms, NV centers, supraconducting devices, silicon impurities, photons. We don't know. Each of these type of qubit has its pros and its cons. The only thing that I can tell you is that I think that photons will survive, but maybe they will not survive so much for doing calculation, but for connecting qubits, because photons are excellent for transporting quantum information from one place to another one. So in my opinion, the structure will be a structure with some qubits that you can keep at a position and photon to connect them. Well, it's just, but at this moment, we don't know any winner taking everything. Another problem, and we have experts in the room here. If I give you tomorrow morning an ideal quantum computer, well, people don't know exactly what to do with it. We have several use cases which are excellent, but we don't have a systematic way to translate a problem into a program, let's call it a program, into a program for an ideal quantum computer. This is why there are so many applied mathematicians working in this field, and I think it is absolutely necessary because it's good to develop a hardware, but you also need to have the people for using the hardware. Quantum simulation. What is quantum simulation? Quantum simulation, in fact, was the initial idea of Feynman. Feynman told you, if you want to calculate the quantum state of electrons in matters, it's absolutely impossible. No computer can handle this amount of information. So there is something you can do, is to replace your electron in matter, which you can hardly look at, by an equivalent system that you can manipulate. This is what we do with ultra-cold atoms. We put, thank you very much. Merci. My voice is fading. You put atoms in a potential that you design, you customize with lasers, and you reproduce the electron in the matter. And with that, you can observe effects that people have never seen directly. For instance, in my lab, we could directly observe Anderson localization. People who have we have taken a photograph of a wave function in Anderson localization. People who know of that will appreciate. So the idea is to mimic a system by a system which is easier to manipulate and to observe. And it turns out, so there are several ways of doing that. One that I like very much is the one of my colleague, well, former student, Antoine Brouès, who is one of the founders of the Société Pascal. Oh, I have a conflict of interest, by the way. I am a co-founder of Pascal. So when I speak well of Pascal, you know that I have an interest in speaking well of Pascal. So I have to declare it, I declare it. So Antoine Brouès can manipulate atoms in 3D, and just to show that he can do anything he wants, he has done an Eiffel Tower. Of course, the Eiffel Tower is not good for anything, except for showing that he can manipulate the atoms and put them in any place. Okay. There are already specific applications demonstrated. For instance, solving problems for physicists. But the problem that physicists cannot solve with a classical computer, you can solve it with a quantum simulator. There is more. It turns out that some problems, usually optimization problems, can be mapped on a situation that you can implement with a quantum simulator. For instance, equilibration of the electric grid, a smart grid. You know the problem. You have a wind here, sun here, and you have a car which has to be loaded here or there, and at each time you must absolutely equilibrate the grid. It is one of these problems that you cannot solve by brute force on a classical computer, even the most powerful. It turns out that by using a quantum simulator, it is possible that you can solve this kind of problem. And so the Société Pascal, I already mentioned it, is at this time having a quantum simulator. Now they are going for an ideal quantum computer, but they have already a quantum simulator. Now we need also programming language, and this is also an open field. Okay, and so to conclude, we here also have some specific applications within reach, I would say. Quantum communication, this works. Quantum communication, you have quantum cryptography, which is quantum key distribution. To make a long story short, in classical cryptography, you must make the assumption that your adversary is not much advanced compared to you, is not more advanced than you, either with mathematical theorem or with computing. If your adversary has computers 1,000 times more powerful than yours, then he or she can decipher what you do on the internet. Your adversary can also have a theorem, a mathematical theorem that we don't know, which allows to factorize number faster than we do. So classical cryptography relies on the hypothesis that the adversary is not much more advanced than you. Quantum cryptography relies on the very basic properties of quantum physics. If one day quantum physics shows that there is a failure somewhere, then be careful. But until that day, then when you have quantum cryptography, it's absolutely secure. It does not depend on the level of your adversary compared to you. And there is also quantum teleportation, which is not Star Trek, which is just transporting quantum information. And there is a problem of range. With optical fibers, you can hardly go beyond 100 kilometers. But our Chinese colleague Jian Wei-Pan has demonstrated that with a satellite, he can send 2 photons, detect them at more than 1,000 kilometers, and make a quantum key distribution at more than 1,000 kilometers. If you add to that a quantum memory, which still is to develop, there are some examples, but not so good. If you have a good quantum memory, what you can do is, I must improve my pointer. Voilà. Let's suppose you have a quantum memory in your satellite. You send a first photon, you keep the second photon in your quantum memory, you let the satellite propagate around the Earth, and then you send the second photon. With that, you can distribute entangled photons all around the Earth. This is difficult, but it's not out of reach. It's not more out of reach than gravitational wave detection 30 years ago. So specific application already available or within which. I'm going beyond my time. I will finish. Quantum sensing. This works really. You have here a quantum gravimeter. You have squeeze light, which allows one to improve the accuracy of some measurements, for instance, precisely in a gravitational wave detection. And you have NV centers, which do beautiful things. Jean-François Roch, who is here, is one of the experts, but there are experts also in NTU of these kind of things. Okay, here really it's working. This is already an industrial apparatus that they put on volcano to measure the fluctuation of gravitation in the hope that they will be able to anticipate eruption, volcanic eruption. Okay, to finish, will the new quantum revolution transform our society? I don't know. I already mentioned the name quantum advantage. I would like to say that when we speak of quantum advantage, we think first of computing power much higher than the kind of computer that we have. But there is another side of the coin. It might well be that with a quantum computer, you can do the same calculation as we already can do, but saving energy, with much less energy. And this must be kept in mind, especially with the young generation, which is so worried by the problem of the planet, etc. If you want to attract young people to work in quantum computing, you better tell them, you know, this is a possibility of the quantum advantage. And so to finish, nobody knows, but there are states, you know, Europe, France, many states in the world putting money in it. Big companies which have a lot of money put a lot of money in research in quantum technologies, and many, many startups, and all this is fascinating prospects. And well, young people who like this kind of physics, don't hesitate to go into it. Thank you very much.
Thank you for the wonderful talk. I think we can also put Pascal in the list. Pascal. Yeah. So we have time for maybe 2 short questions.
Hello, Dr. Speck. I'm not quite good in physics when I was in school, so.
Don't tell me that.
Yes.
Don't be proud of it.
I'm not so proud.
Good.
So the question will be, yes, in the beginning we thought like, okay, for the 2 photon or even quantums entangled in different places, we thought, okay, there might be a dream that we could maybe overlap speed somewhere and do this concurrent, simultaneously communications. But right now, maybe we understood that might not be possible. So what do you think in the future would that be still possible in some other ways that could help to lower the latencies between the geographical distance?
No, it's absolutely not the point.
Yeah.
Non-locality cannot be used for transmission of a useful signal.
Yes.
So you are going to tell me, but what is the point? The point is that by thinking about non-locality, you think that you can transport quantum information. And transport quantum information is something extraordinary, because if I have here a system, it has a quantum state. The quantum information is a quantum state. But we know, this is a basic principle of quantum mechanics, that I cannot know that quantum state. If I try to measure it, I destroy a part of the information. Quantum teleportation, which is done thanks to entanglement, is the fact that I can take that quantum state, and without knowing it, I can put it here. And here, now, it's erased, because otherwise it would violate some basic principle. But now let us think that we have a quantum computer here. It gives a result, and this result, I want to use it for a second quantum computer. Quantum teleportation is the solution. So the non-locality in itself just draws the attention on the fact that there is something extraordinary. Now, because you asked me that question, I will take the opportunity to tell you something. I do an experiment in which I think that there is no locality, but I cannot use it to transmit a useful signal. But I register everything. For instance, the experiment I did 40 years ago. I register everything. When it is finished, I look at what happened. I do something like an historian, like an archaeologist. I look back in what happened. And when I look back into what happened, yes, something did happen instantaneously. I could not use it on the spot, but something did happen instantaneously. But again, I think that the most interesting part of it is to put the finger on the fact that you can do things extraordinary with it. For instance, quantum teleportation. For instance, distribution of quantum key for cryptography.
Thank you so much.
Okay. Do we have another short questions? Right.
Hello. So thank you very much for a very wonderful talk. So I have basically 2 questions. Sorry for additional one.
Is he allowed to have 2?
So the first one would be like,
As long as it's short.
can you comment a little bit on the quantum network? I mean, yeah. And the other question is that since we all know that basically after EPR they announced their debate, so until John Bayer proposed his famous inequality, actually, as you mentioned, all the people think it's just philosophy. No physics take care about what happened over there. But what kind? But my question would be like, after John Bayer, why you be interested on this topic? Because I can imagine at that moment it should be more interesting. Okay, maybe more fancy stuff. Probably all the people will be interested in, but you still want to do this experiment. So this is my second question.
Okay, there is my point of view and there is a general interest. My personal interest is, when I read Einstein, I think that it is crystal clear. And it's hard to accept the idea that Einstein might be wrong. On the other hand, when I read Bohr, it's absolutely unclear, but he has a fantastic vision and intuition. And so you have this situation. You have Bohr, who is not clear. You have Einstein, who is crystal clear, and they have opposite conclusion. I have a chance to settle the debate. I found it fantastic. Now the benefit, well, first there is not benefit for everybody. There are some physicists belonging to the school of shut up and calculate. Most of them are like that. They say, I just do the calculation, I look at the result, period. I think that in fact there are more people that would admit it who need images. I need images. I tell you I need images for my intuition. And in my images, I have non-locality. And the reason why I have non-locality in my images is because I did that experiment. And I can tell you, my image is fruitful. I can show you immediately why in quantum teleportation you need a quantum memory. You need a quantum memory because of the non-locality. And so when people do demonstration of quantum teleportation without taking that into care, their system will never work as they do it. And this, I can do long calculation, but I see it immediately because I have this intuition. So even if you are not interested in fundament, in discussion between Einstein, it is very useful to demonstrate directly by an experiment that feature. In addition, there was a chance that it would have been a limit of quantum physics. Everybody reasonable thinks that sooner or later we will find a limit. The limit could have been at the point where there is a conflict between Bell's inequality and the prediction of quantum physics. Well, it's not the case.
Okay. I think we have enjoyed a very wonderful talk. Let's thank Professor Esbeck again.
Thank you.
Actually in FastCon, we do excellent research on quantum error corrections.
What I expect to do is to know more what you do in Foxconn, and then I will add Foxconn on my list.
Yes. Wonderful.
On the list of rich companies.
Yes. Yes. So we have a booth over there. Please, if you are interested in what we quantum computing teams are doing in Foxconn, please visit us there. We have wonderful results.
And can I advertise? It's a book, Einstein and the Quantum Revolution, translated in Chinese. just published.
Yeah. Thank you.